Okay, now that we've talked about structural, or looking at the code, and just analyzing the program statements, the next thing we need to talk about is at least just data flow testing. Beforehand, we're talking about control structure executing one statement on another. What data flow testing is going to look at is how can the data actually change what test cases you should have. Fortunately, what this is going to resolve to is this is how you would look at data flow testing, and then we're going to see that it's very, very difficult to actually derive strong numbers from data flow due to how our programming languages are set up. So you understand why it is, recognize the basics of data flow, understand how infeasible this problem can be, and basically understand that data flow unfortunately has a limited application due to its difficulty. So far we've talked about node and edge coverage. Maybe that doesn't cover all the interactions. We want to look at some middle ground here. We looked at path-based, of course, but we want to look at, okay, maybe not just, is there anything between this basic statement coverage or branch coverage and the full-on system testing? Is there anything else we can actually look at inside of structural testing? Intuitively, if you look at it, statements interact through the data they flow, so maybe we can do some evaluations of the values of statements. And really only bad value computation is revealed when it's used. Usually your program, most programmers are programming for the happy path. They assume that their users put in correct data and then they write their code for it. So really we want to look at it from a data value. What happens when we put in a rogue data values or data values that are not anticipated? Alright, so let's look at least the concept. It really comes down to these definition use pairs. For example, if you have value 1, at statement 1 and your flow is 1, 2, 3, 5, 6, then it's defined at 1 and then used at 6. Another one may be, since x is defined at 4, it might be 4, 5, 6 and defined here. So it may be, so definition use pairs is one where it's defined and the second one is where it's actually used. Since you have definitions at 1 and 4, that can be the start of a definition use pair, and then 6 if there's nothing in between. Alright, so let's go make sure we get the terms. These are straight from the book. A pair of definition and use for some variables such as at least one DU path exists for the definition to the use. The path is a definition clear path in the CFG. What does definition clear mean? The value is not replaced. This makes a lot more sense from a picture. So 1, 2, 3, 5, 6 is a clear path because x is defined at 1. It's not redefined at all the way up to its use. 1, 2, 4, 5, 6 is not clear because it's redefined at 4. So this is not a good definition use. You can think of the value of x as killed at this moment. Better way of thinking about it might be reassigned. Still, 1, 6 is a definition use pair because you could flow 1, 2, 3, 5, 6. So that's still a legal definition use pair. You would just know that if you're going to use this as a definition use pair, this is the path you would have to take. So if we're going to do adequacy criteria, once you come up with these definition use pairs, just make sure each definition use is exercised by at least one test case. Each simple non-looping DUs pair is executed by one test case. That shouldn't be too hard, aka non-looping. There's a keyword there. And just make sure there's a test case. Fortunately, this can become extremely difficult. For example, you have x sub 1 equals etc., and then later you have y equals x sub j. Well, this may be a definition use pair only if I equals j, what I was here and j was here, because somewhere in between I and j could change until you get to these two. So technically that's a definition use pair. That might be a little hard to see. What makes this even harder is with programming languages that use pointers, which most do. Some of them try and hide it from you, but in the background they're still using a pointer to implement everything. It's just the way computers work. Well, if p equals some address of x, and then later you have p equals x, then you use x later on, well, hopefully you would have to look at the aliasing and see from here you get pretty clear that x is defined at this statement and then used here. Fortunately, if you're doing pointer arithmetic, this can become extremely difficult to do analysis on, because if you take a pointer at some address and you move your pointer around a bunch, and then that's where you change the value here, which happened to be what x was, it can become very difficult to see that inside of a compiler. And then even simple objects, because this is what I'm talking about, where pointers are actually being used. These are different objects. It's hiding pointers from you to make it easy, your code easier, but it's still the same thing. How do you know if M and N are the same object? How do you know they're pointing to the same object? Do M and M also share a common foo field? So the problem here is aliasing, which references are always or sometimes the same. So arrays and pointers are critical for this flow analysis. Underestimating the aliasing may fail to include some of your pairs. Overestimating may introduce unfeasible test obligations into your program. So you want to come up with something exact. Hopefully you can see from the past that since we now have to do pointer arithmetic evaluation or object referencing evaluation, which basically resolves to pointer arithmetic, this can come into what essentially is a halting problem inside of this problem, and therefore it can become pretty infeasible pretty quickly. So you may need to either estimate, underestimate, or overestimate, but unfortunately both of those do not have outcomes that we like, because underestimate will miss some DU pairs, overestimate may introduce something that's infeasible. May be preferable to accept underestimation of aliases, because in reality, when you're looking at this from a test suite, you're just trying to come up with additional test cases to improve your confidence that your code is working to the quality that you desire. So it may be you may be able to underestimate it rather than overestimate it, but this can be different if you have a compiler which needs to be correct. Then conservative overestimations is usually required. So that kind of limits what the compiler can actually produce in the end. Aliases may rely on external guidance or other global analysis, so it may just not be a section of code. Something else in the program may be changing its state. And what it comes down to is undisciplined use of these dynamic storage, pointer arithmetic, etc., can make this infeasible. That's what I was talking about earlier with the halting problem. Just to make sure the feasibility is a little clearer. Suppose a condition has not changed between 1 and 5. Well, that's great. That makes it easy. Then 3, 5 is definitely a definition use pair, or 3, 6 here. But it's difficult or impossible to determine which pairs are actually feasible. Do you actually know that you can get here from that condition and then maybe jump to true over here? I mean, this condition was false. Did something here change the condition so you can move over here? Now you got to do a condition analysis, which, again, halting problem embedded in your program. Infeasible test obligations are a problem because no test case can actually cover them. Hopefully y'all see what the issue is here. So the path-oriented nature of data flow makes it infeasible. Another way to think of it, I was saying it's a halting problem, but another way to think of it is previously we were talking about paths. Once a data flow can change the number of paths that can be taken, you're also having to do path analysis. So that can make it very practical. In practice, reasonable coverage is often or not always achievable. Here's the problem right here: is reasonable. Is it actually reasonable for what your program? I mean, you're just writing an application on Android. You may not need, you don't need perfect DU data flow coverage. On the other hand, if it's a medical device, you're probably going to be looking at full coverage here. Could be exponential at worst. Often, though, if you set up your code correctly, it becomes linear, and therefore you can actually do the full analysis. All DU paths is often more impractical, so you can't do all DU paths unless you've written your code a certain way. All right, summary. What you really need to draw from here, and you're going to go through your homework and do a couple of examples here with data use pairs and whatnot. But the point here is that data flow analysis can give you some test cases, but keep in mind that this can become an exponentially hard problem, which means that doing perfect data flow analysis is not in general a pragmatic approach to things, although doing data flow analysis can give you additional test cases or insights to add to your regression test suite. And the reason for the limits come from the aliasing or infeasible paths. All right, that's it for this week.